We will start. A reminder that this Thursday is the first midterm, and you should have already got an email describe how you're going to take it on Canvas. So today I'm going to add an extra office hour at 7 p.m. Pacific time to hopefully that for outside the country also have a chance to join. Okay, so the midterm covers everything from lecture 1 to lecture 8. So what I'm going to talk about today will be in the second midterm, not in the first midterm. Okay, so what do we want to talk about? Well, now remember that we have previously seen the so-called the following set operations. So imagine that you have a database indexed by some keys, and you want to support those operations, which includes things like search for an element, or find the maximum of all the keys, the entry with the largest key, and so on. So these are all the so-called static operations, okay? And imagine that you also have, you want to insert new elements into the database, or you want to delete the existing one, or you want to extract the one with the maximum key, and so on. So this is so-called dynamic operations. And what we said last time is that for this kind of set operations, we can use a balanced binary search tree, okay? And when we use a balanced binary search tree to keep the height low, then all of these operations can be answered in a log n worst case time. Okay, so it's very efficient, and the data structure is not hard to maintain. Essentially, you have to maintain a tree structure. Okay, the question is that, can we do better? So for example, suppose you know that for the operations that you have at end, the only operation you need is so-called dictionary operations. Okay, so which means that we want to, let's say, suppose we're given a universe of elements U, imagine that these are all the possible, say, words in English language, okay? And suppose you want to store a subset of them. Say you want to store all the words appeared in the specific paper, okay? And assume that the operations that you're interested in are a search. This is so-called membership query that we're very familiar with. Given the specific word you want to know, is it in this paper? Did it appear in this paper? Okay, do I have it in our input? Or you want to insert a new word, or you want to delete a word. Okay, you want to, these are the three operations you would like to have. Okay, so we call this a dictionary operations. Okay, all right. Now, for such operations, of course, we can still using the balanced binary search tree to help us to perform all these operations. And we know that the worst case time complexity is pretty decent, is log of m, okay? Much better than the linear time, okay? But can we do better? In particular, can we have a lighter weight data structure? Okay, so binary search tree is not hard, but still you have to maintain all the pointers. You have to, every node, you have to maintain the left child and right child, and you also have to make sure that the binary search tree property holds at any moment. And for the balanced binary search tree, you also have to do adjustment, do this rebalancing to keep the height low, keep the height balanced. Okay, so it's not a super lightweight data structure. Okay, so can we have a more efficient way to handle if these are all the operations that we care about? Okay, and that's what we want to do today. Okay, we're going to introduce something called the hash table to do this. Okay, and before that, we'll first talk about the idea of hashing in general. Okay, all right. So let's first look at the idea of hashing. This is actually a quite common and important idea, used a lot in practice, although you may not have noticed that we're using them, okay? So it has many usages. What we will later talk about is to support a faster query in a large data set. So this is what we'll focus on later using the hash table, okay? But the hashing idea has been used in other places as well, such as to verify the integrity of messages, to identify whether the file has been changed in version control, and so on. Okay, so let me give you some examples. Let's say that but first, so what is hashing? Okay, so a hash function mathematically is simply just a function going from your universe to another set x. So the x can be integers, or all the integers from 0 to 100, let's say, okay, to a smaller set, okay? So that's it. That's a hash function, going from a function from one set, so the first one is a universe, to another set, okay? But to make this hash function useful in practice, okay, ideally what you want is that your universe could be huge, okay? You could potentially have a large and complex set, okay? You want to map it to a much smaller and simpler fingerprint of that, a signature. Okay, we're going to see examples in a minute. Okay, so this is usually what you want to use a hash function for. Okay, and also ideally, you want this mapping to be kind of uniform, so that not too many, because you are now mapping a big space to a smaller space. Okay, so we don't want too many of the elements got mapped to the same image. So you want to cause very few collisions. Okay, and note that a hash function needs to be deterministic. Okay, namely, when you hash the same objects twice, okay, it has to get the same answer for it to be useful. Okay, all right. So now let's look at some examples. The first is a so-called cryptographic hash function. Okay, so essentially, it can map data of different arbitrary size to another, very often fixed size output of much smaller size. Okay. So for example, MD5 map an input, say potentially a very long string, can be a whole document, into a fixed 128-bit value. Okay, and why do I want to use for the cryptographic hash function to be useful? You want to make sure, so these two properties are not necessarily for general hash function, but they are important for cryptographic hash function. Okay, you want your hash function to be hard to reverse engineer. Namely, if I present you the 180-bit value, it's hard for you to figure out who got mapped to this one. Okay, so it's hard for you to reverse engineer it. Okay, another one is that you have two similar input. Okay, they can actually lead to very different hash value. This is ideal. You actually want this property because you don't want to say that, okay, if I have two strings very similar, then they got mapped to very similar output. Okay, because then if I manage to decipher one of them, then there's a good chance I can decipher the other. Okay, so you don't want this. Okay, you want, even when input is similar, you want them to be mapped to things output which can be very different. Okay, so here are just some examples. For example, in Python, you can use apply MD5. You can map the string, my name is Justin, to the following hash value. Okay, and if you say that my input is my name is Justin, but with the exclamation mark in the end, okay, the difference is minor, but you see that the output can be very different. The goal of this is so that people cannot just by, even if they know this actually represent my name is Justin, they cannot decipher this because there's the output are quite independent, quite different. Okay, it's hard for them to reverse engineer. Okay, as I mentioned earlier, you can in fact hash a whole document into a fixed size output. So input can be complex and large, but then using this cryptographic hash function, you hash into a much smaller fingerprint. Okay, now there are two advantages of using this cryptographic hash function. Number one, you can map something very complicated to a small output, so it's easier for you to store, for you to check, and so on. Number two is that this is it's encoded into this output, and it's hard to reverse engineer. Okay, so you may ask that why do I care? Why do I want to use this? Well, imagine that suppose I release a piece of software, okay, and I host it. I release it publicly. I host it on my Google Drive. Okay, but someone, maybe some malicious person that decide to insert some extra code into my software or to spy on users and so on. Okay, in general, how do I know that the code has been changed? Okay, I have no way of knowing. So what do I do? Well, what I could do is the following. I could release the software together with the hash value. I hash it and publish only the hash value. Kind of you encode it into a small string now. Okay, and I still release both of them, hosted public on my Google Drive. Now, if someone insert extra code into the software, okay, then when you download the software, okay, you don't immediately use it. You first hash it again, okay? Then you compare the two hash values. If your hash value is very different from mine, that means that the file has been changed. Okay, so this is now note that releasing the hash value, since the reverse engineering is so hard, releasing the hash value doesn't really give people, they don't know how the hash works. Okay, they cannot say engineering to modify the software so that you still have the same hash value, basically. Okay, so this is the typical use of this cryptographic hash function. Okay, well, another simple example. Okay, let's say that you have a huge amount of images and you want to put them into different bins to organize them. Okay, and but how do you decide which bin you want to then use an algorithm to retrieve those images? But how do you decide which bin an image should go to? An image is a complicated, say 128 by 128 map, which has so many pixels. Okay, so how do I store it in the array? Let's say. Okay, so what we can do is that to decide which bin it goes to, we can again use the hash function, which hash your input, say 128 by 128 image into a number, into an integer, okay, from 1 to 100. And then once I have this hash function, now it's easier for me to index that. Then I can put it in the corresponding bin. Okay, so this shows another advantage of using hashing, which is that you don't have to work with numbers. Your input can be numbers, can be images, can be other complicated objects like documents, a string, and so on. Okay, then you can use a hash function to convert it into an image and then say index it and so on. Okay, all right. So this is the general idea of using a hash function. Again, just to remind you, a hash function is simply a function from one set to another set. Okay,